record this session, we are talking about now the measurement worksheet. And we started by talking about increments and saying that the increment is the distance between two values on a measuring device, and the amount by which a measurement changes with precise scale. It's the distance between the marks. Okay. Now, precision of measurement, as I was saying from Google, the definition of precision of measurement refers to how close an agreement is between related measurements. So let's literally write that out. How close an agreement there is between similar measurements. Now, what that actually means? Well, that means essentially how within the same ballpark, how within the same neighborhood are different measurements when they are taken. And that is why, if I'm really going to do this accurately, I'm going to do this with the full picture and full disclosure of information to you. What we really should do is actually pull up the classic definition that I was just giving. Well, not definition, the classic analogy that I just mentioned, accuracy versus precision. We should just go ahead and go there. And the reason for that is it does actually, in my mind, help with gaining a better, more clear understanding of what we're trying to say here. Yeah, and it's never a perfect system, far from it, but here comes the slides now. Okay, so this is the analogy I was talking about. Okay, now we're going to go to one slide forward, even from here, like so, and let's define, I know I'm jumping around a bit, I do apologize, precision as the closeness or proximity of measurements taken for the same measured, we'll say thing. Like if you're trying to measure how much water is in a glass, you measure it several times and you may get several slightly different values. That makes sense?
Yeah.
Okay, so several measurements of a quantity of mass or of the ambient temperature using maybe a couple of different thermometers, a couple of different sources. Now, how close do those measurements fall to one another? Because we've taken different measurements of the same thing. So we want to know how close are they to each other, because ultimately the goal is to actually determine what is the quote unquote real value, right? We're trying to determine what is the real value. We can't just come up with a number. We have to actually determine it some way. So we measure it several times and then statistically say, to our best effort to measure, this is what we think the real value is. Does that make any sense?
A little bit. I was kind of confused on how you wrote the question. How close are those different measurements of the same? Like, are you like I think I just needed it worded a little bit different. Maybe that's
Okay. So
yeah.
I got a message from someone asking, does precise mean consistent? And essentially, that is not a bad synonym. Yeah. When we're talking about precision of measurement, another way of kind of relating, it's not perfect, but it is a pretty good synonym. How consistent are your efforts at measurement or your measurements? Okay. Now, keep that in mind when I jump to the next slide and say accuracy. So accuracy typically is said to be how close is a measurement to the actual, what we would essentially say, real value. And no, we're not going to go into the philosophical implications of saying that there is only one real value, but you have to measure it. And you're now trying to determine how close are your measurements to that real value when the measurements are the only way that you can determine that real value. That is a absolute circular philosophical, it'll mess with you. But how close is a measurement to the actual accepted real value? How do we determine a real value? Generally, a real value is taken as a statistical, quote unquote, average of tons of data. You do a ton of data collection of the same thing. If you were talking about, okay, we're going to say this is 1 gram of water, you would measure it 1,000 times and then compare those measurements to each other and take the average of that. And that gives you some idea of how we start to head in the direction of saying this is a real value. It is mind-numbing work, but it is important because we do have to have standards. We do have to say this is a gram, and when you measure a gram, it will always be 1 gram. Otherwise, we have nothing to compare. That makes sense?
Yeah.
Okay, so what we're saying then is how close is an individual measurement? That's just single E there with an M, and that's just getting worse. So how close is an individual measurement to the accepted real value? Just like we're always continuing to calculate pi to a further decimal place and get it more accurate. Same thing can be said of any real value. We continue to refine and refine and refine. So how close is a individual measurement to an accepted real value? That's accuracy. Precision is the closeness of a measure of a series of measurements to each other. And so that takes me to the dartboard analogy, which is not great, but it's an analogy of sorts. So this analogy, hopefully you can see it, you can be accurate and precise. You can be not accurate, but precise. You can be accurate, not precise, and not accurate and not precise. The idea is precision is how close the darts are to each other. And accuracy would be how close a dart is to the center of the bullseye. So individual dart hits the exact center of the bullseye. That is a perfectly accurate throw. The further an individual dart is from that center of the bullseye, the less accurate it is. The closer the darts group to each other, the more precise your measurement ability is. And the further apart the darts are from each other, the less precision you have, the less precise you are. How is that? More confusing, or does it make sense?
Makes a lot more sense.
Okay. For two words that get used often by people to mean the same exact thing, you can see why it actually does matter how you use these words, at least when it comes to science. They do mean somewhat different things. So if we keep that in mind, then the difference between accuracy and precision, then when you are asked, this is a very long way, I know, to get to explaining precision of measurement, but I feel like if I explain it very carefully, we might get to a better understanding of it. So the precision of measurement, when it comes to this worksheet, is asking how close can your measurements be to each other? And therefore, it's going to be the decimal place to which you estimate your measurement. And what that means is your precision is one further saying division is not quite perfect. One further, the best way of saying it is something along the lines of decimal place or approximate change, unit of change, that you go beyond the smallest increment. Now, does that make any sense at all?
Yes.
Okay. So if that does make sense, then looking at number one, what is your precision of measurement?
Would that be, so then one further decimal place? Wouldn't that still be one?
One further decimal place.
One further decimal place. Oh. Okay. Okay, maybe I got lost there.
Okay.
One.
So the question is, well, a number of things, but first of all, the first question is, do you know where you got lost?
I think I I think when you were talking about the decimal place to which you estimate your measurement, so am I looking at like that bar above the measuring device and then going from there? So that's the next decimal place from that point, or is it from like where the first smallest increment is? Like, is it? I think that's where I'm getting lost.
Trying to see if I can find some very quick examples that could be useful. Let's see here. Okay. Because I don't want to keep leaning on the homework.
Yeah.
So I found a couple of images. Let's try this out real quickly. I'm going to temporarily unshare that slide. So the screen should be blank for you guys now, I think. Let's try a couple of quick examples here. There's an example. And that. Give me a couple of other things. Come on. Copy that image. There's that one. Come on. A couple more measurements. Okay, so I guess 2 examples. Do this. Oh, that's a good one. Okay, so here we go, resharing, and there's that, and here is this one. Okay, so you can see a leaf now on the screen. Okay, so the general idea of what I want to come across here is, let's say I ask you, looking at this, to determine the, this is not perfect, it's kind of fails to some degree, but with these rulers, let's say I wanted you to measure how far it is from 0 to this spot. Okay, and you see it kind of drops onto the ruler right there, right? Still, well, okay, yeah, we're gonna go with this because I don't want to waste time with more examples. So you can see that this is similar to an example we have on the assignment. What is this to begin with? What is the smallest increment?
Would it be the 1/10 of a centimeter?
Yes. Yeah,
Okay.
0.1 centimeter. Absolutely. Yeah. And as you can see, that is because that is the distance between the smallest marks. Exactly.
Mhm.
Now, the precision of your measurement in general is going to be 1/10 of your increment. It's not always that, but in general, it's going to be, in general, it's going to be 1/10 of your increment. So what is 1/10 of your increment?
Um, 0.01.
Yes, 0.01 centimeters. And that's the precision of your measurement.
Oh,
Because
okay.
Because if you look carefully here, you have to now estimate, because the steps you go through to actually coming up with a measured value, if we are doing it, let's make it measuring 1. Read the device to its smallest increment. So to do that, you would then see this as 5, somewhere between, you're going to see that the actual measurement will be, the measured value is going to be between 0, not 0, sorry. It's going to be between 5.1 to 5.2. Then estimate one more decimal place, because we know it's between 5.1 and 5.2. The only way to convey that is to actually concretely lay down an effort to measure something between 5.1 and 5.2. So we would probably say, not 5.2. We would say, since it's between 5.1 and 5.2, the first 2 significant figures are 5 and then the 1. And our last significant figure is going to be the value occurring to our estimate. And here I would typically estimate this at 5.15 centimeters. Now, here's a note as an aside to this. If you are measuring a value, and say we're doing it, now let's do it in yellow here. No, yellow is going to be horrible. I want it. So let's say we're measuring a value and it looks like it falls exactly right there. Okay, so it looks like it's exactly on an increment. Then you estimate this is getting bad, a 0, and your value would be 3.00 centimeters. If you say that it is exactly on 3, you still have to estimate to that 100th place, because that is the level of precision that that measurement device is capable of. All right, any questions about that? Okay, if there are no questions about that, does anyone need more time with this slide?
So if I'm getting this correctly, our precision of measurement goes off of our increments. So it's basically like moving towards like, so if it's the increments at the 10th place, then the precision of measurement will be at the 100th place.
Exactly. That's all there really is to it. It's not a super complex definition. Yeah.
Okay. And so
at least I hope it doesn't feel complex. Yeah.
No worries. And let's say if a number was at the hundredth place, would the precision measurement be at like, let's say like the ones place?
So you can't go into a larger increment because it doesn't make any sense to, if you can see clearly to the ones place, to then estimate your measurement to saying, well, I know that I can measure this with perfect precision to the ones place. So my value is 15, but you know what? I'm just going to estimate it somewhere between 10 and 20.
Mm-hmm.
Does that make sense what I'm trying to say?
Yes.
You're always going to go one for your precision of measurement and the last significant figure that you're recording for your measurement. You're always going to go one further step to the right. You're going to go one more decimal place smaller. You always go one decimal place smaller because that is where you can no longer say with perfect precision, I can measure it being here. You are saying I'm estimating it to this place.
Okay. Gotcha. Thank you.
No problem. Thank you for asking. Okay. Any other questions? Any other questions? Okay, nothing in the chat. Okay, if there are no other questions, then I'll go on to the next example that I have pulled up. Here is the next example. And so instead of me doing the work on this one, I want you guys to try to tell me first, determine the smallest increment. And there's a reason we're asking smallest increment and not largest increment. The reason we're asking smallest increment is because your precision of measurement, like I said, comes from going one further decimal to the right of the smallest increment. So we're asking, okay, what is the smallest increment? So that you can then next say, I now need to move one decimal place to the right of the smallest increment. So what is your smallest increment? Oh, wow, apparently it's falling off the page. So what is your smallest increment? Let's try creating a somewhat straight line. And then the precision of measurement, of course, we could even call that just the level of precision. They mean essentially the same thing. They are synonyms. So what is the smallest increment on this one? And it's not a trick question. If it feels easy, it actually can be. If it's starting to feel easier, then that's good. And that just means we're making progress.
Is this 1/10 of a centimeter?
A 1/10 of a centimeter, precisely, yes. You are looking at 0.1 centimeter. And I realized after turning page that I essentially had found a similar ruler to what we had just looked at. But that's okay. The repetition may be important. So what is the precision of our measurement? The smallest increment is still going, it's not determined by the value that is actually labeled. It's going to be determined, and I'm saying this because of a direct message I received from someone here. The increment is determined by the smallest increment or smallest distance between two of the clearly indicated demarcations. It doesn't matter whether they are clearly labeled with a numeric value in this fashion. They still are clearly indicated, demarked increments. Now, the precision of measurement becomes
0.01.
precisely, or I should say correct, 0.01 centimeter. I'm going to make sure I try to choose my words very carefully to convey the meaning I am going for. Yes, so your precision of measurement is 0.01, which means your last significant figure will be the second decimal place right of the decimal itself. So what is the actual measurement of this gray object then? It's going to fall right about there. I would get for that something about 1 point. It's between 3 and 4 when it comes to that. Sorry, 0.3 and 0.4. So it has to be 1.3, and we'll just call it 1.36 is what I would tend to call it. You could call it 1.37. That is also a viable option. That is why we say that the level of precision, the proximity of our answers is going to be to the 0.01, because there can be some variation in how people see these things. If we had said that we were just going to take the value of 1.3, no one would be able to disagree. And yes, there was a comment sent to me that saying it's precise, but not perfectly accurate, because the value cannot actually be determined to that second decimal place with flawless accuracy. We cannot say that this is the true value. So the measured value is somewhere between 1.36 to perhaps 1.37. This is going to be, of course, in units of centimeters. And therefore, finally, the last thing on there is the number of significant figures. And you can see we have 1, 2, 3. Now, I received the question, is there a situation in which the smallest increment will be 0.5? That is an interesting question. And to answer that, it is theoretically possible. Typically, we don't tend to utilize that, but let me think if I can come up with an image that might work with that. If we had a ruler or a measuring device, whatever you want to call it, and say we had the value of 1 right there, and on that you then had the value 2, was very close, and it's extremely hard to see on that value whether a value that falls like so, right in between 1 and 2, is anything further than either halfway between or on the value itself. Does that make sense? If you look at this thing, it's 1, then it's 2, and this thing that I'm trying to measure is about in the middle. And so all we can really do is go, okay, that's probably 1.5. It's not perfect, because increments we tend to utilize are base 10. That's just the system we utilize. We utilize a base 10 system. And therefore, we will tend to go in increments of 10, units of 10 within that decimal place. However, situations may call for something that will be generally a increment of 0.5, because here you can't really say, well, it's actually probably 1.4. If it looks like it's in between those two and they are so close, you're very likely going to just say, no, it's 1.5. It's not 1.4 or 1.6. I would call that 1.5. I hope that makes sense. Okay, we have spent quite a bit of time on this topic. I would actually like to try to answer some other questions. Is that all right with you guys?
Yeah, I'm good.
Okay, then I have received a direct message requesting that I look at homework question 2.91, specifically C. Let me see if I can grab my copy of the books very quickly. Okay, I am not entirely certain where I set my book, and I don't want to spend a lot of time looking for it. So give me 1 second. The question is, how can you locate the element if it is... Okay, so this is a question about electron configurations. Okay, so this is now homework question number 2.91, letter C. And the question is, what element is determined by electron configuration for okay, I should say electron configuration ending in 4d5, 5s1. Okay, so given that question, the fastest way to answer it, giving not just the fastest way to answer it, but the most effective way to convey how I would figure that out is, to begin with, you are looking at, this is the highest primary energy level. This is the shell we're filling. Now, how do I know that? Well, it comes from understanding how the electron shells fill. So, the long story short, the way the shells fill, even if we were going to ignore the periodic table, they fill 1s to 2s, and then to 2p, 3s, 3p, 4s, and then after 4s comes 3d. I think, yeah, 4s, 3d, 4p, 5s, 4d. This is how they actually fill up as you fill electron shells from lowest energy to highest. Okay, that's the progression you go through. Now, if you guys are with me so far, if this makes sense at all, that's a good first place to be. The next thing is the periodic table actually progresses left to right and then next row this fashion. So if I can find the image I am looking for quickly enough. There it is. Let's see. Yes, that's probably the best quick image I'm going to find. Let's go with this picture. And in a second, you guys will see what I'm talking about. Because I will share it back with you. Here's the presentation, share it again. So we start out, it's kind of like how you start on a board game. You start filling your electron shells here. This is the lowest energy, if you will, start. Oh, come on, go away. Sometimes it is not convenient to teach online. So we're talking about lowest energy start position on the periodic table, and you move horizontally. You move to play this game, to play the electron configuration game, you move to the right. You always move right until you reach the end of the periodic table. Then you go down back to the starting side. And you start filling again across. And you keep filling across and across and across. And what you do is you have, so if I were looking for an atom over here or an atom over here, then you literally start writing the electron configuration. 1s2, 2s2, 2p6, 3s2. See, 1s2, then I go across, okay, 2s, I can fill that up with 2. Then it's 2p6, I fill all the way up, because if I have enough electrons, then it's going to be filled up. Then I go 3s2, then I go 3p6, so 3p6. Then I find my way, if I'm trying to go down to this element right here. Let's say I'm trying to reach this element right here. I go 3p6, then I go 4s2, and then I go 3d10, and then I go 4p6, and then 5s2, and then 4d10, and 5p4. Now, I know this does not directly answer the question. That is kind of what I'm trying to get to. So you guys see in general how things are filling? Get the general idea?
Yeah.
Okay, so if that is a place where you guys are starting to reach, then there's a couple of caveats to our situation here. We're asking about 5. If the last 2 energy levels that we filled are, what about the last 2 being 4d5, 5s1? Because you're probably thinking, well, If you're thinking about this the way that I am, you're thinking, okay, there's a problem here. Wait. I should do a capital D. That'll drive me crazy. Doesn't 5s fill up before 4D? And in general, that's true. However, like anything, there are exceptions. What actually has happened here? What has happened here is, in this situation here, it started, so this atom started as absolutely what you'd expect, 5s2 4d4. That's what you'd expect. However, an electron decided it was more comfortable in the luxurious 4d orbitals, where it doesn't have to share, because there's actually 5 of those 4d orbitals. And so therefore, each electron, when we move that down, each electron currently has its own orbital, its own private residence. Because of that, there are situations where electrons will actually jump around. These are called the exceptions to electron configurations. So what happened was it moved from 5s into an empty 4d orbital. Okay, so that does mean you can still figure out what the element is. All you have to do is actually just shift the basically work backwards. Okay, now are you guys with me so far?
Yes.
Okay, if you are confused, that's okay. You have time to A, receive extra help, and B, of course, study more. Practice, practice, practice. But for the sake of brevity, because I know I'm starting to run out of time. Actually, I have run out of time, haven't I? Here's what we're going to do. I'm going to put up one more image, answer the question, and then I guess, unfortunately, we have to call it a night. There's never enough time, of course. So, images, just give me a bloody periodic table. Come on. There we go. Copy image, post it into here. How the heck did it become so tiny? That's ridiculous. Of course, everything works out in that way. So essentially, what you need to do is look at the periodic table. And let me put that up in front of you guys real quick here. Boom, boom. And then reshare with the group. Presentation. So here we are. Okay, periodic table. This is one On the main group, it's 1, 2, 3, 4, 5, 6, 7. In the D block here, this is D block. This is going to be annoying. I know. This is 3, 4, 5, 6, because they are one less than the primary group. And back to the primary group, 1, 2, 3, 4, 5, 6, 7. So again, just as a reminder, 5s1 for D5 was the final thing we looked at. This is the final situation. Moving backwards, we would reassemble this to 5s2 for D4. So 5s2 would bring us to this area right here, 5s2, then 4d1, 4d2, 3, 4d4, 3, 4d4, which puts us at the element that I just wrote over. This one right here. This is our final answer. The answer is, I think you spell it this way, molybdenum. I think that's it. Yes, that's the element right there, determined by the electron configuration that we were given.
I see.
Does that make any sense?
Yeah, I kind of get it. So you're basically adding one more electron to the s orbital because that electron likes to move around is what I'm getting at.
Exactly.
Okay. And so work backwards, add those electrons back into the s orbital, and then just do it as normal is.
Exactly. Yeah. If you see something that doesn't make sense, that means you actually need to move one electron back up to where it had come from. 5s1 4d5 makes no actual general sense with the standard rules of writing out an electron configuration. It only makes sense from the perspective of how does this thing actually exist when it's in its lowest energy state.
Okay. I think I'm getting a little bit more used to this.
Good. All right, guys, I am sorry. I'm 5 minutes over. This is time I'm not getting paid for, so I'm going to call it a night. And not that it's about the money, but of course, I just need to make sure that, we're clear. An hour of office hours today is what I'm here for. Have a good night.
All right. Thank you so much. Have a great
You
night.
bet. Bye.